The term spontaneous is used to describe processes that occur without any outside assistance. That is, they happen on their own, whether you like it or not. Spontaneous does not mean fast. It means that the laws of thermodynamics favor the process occurring, so the term thermodynamically favored is preferred. Kinetics uses collision theory and rate laws to make predictions about the rates of chemical reactions. Thermodynamics predicts whether a reaction will occur at all, and in which direction. Thermodynamics does not give any information about how much time is required for the process to occur. For example, the laws of thermodynamics predict that a diamond will spontaneously turn into graphite, but this process is incredibly slow, so it doesn't really happen. We say in this case that the process is under kinetic control, to signify that it is thermodynamically favored, but too slow to occur in any observable way. Early in the development of thermodynamics, proponents were convinced that a process would be thermodynamically favored only if it were exothermic. That's not the case. Exothermicity is only one of the factors that determines whether a process is thermodynamically favored. In fact, it is often a very important factor, and many thermodynamically favored processes are indeed exothermic. But it's not the only factor. There's more to this story. For example, melting is definitely an endothermic process, but if you put an ice cube on the counter at room temperature, it'll melt on its own with no outside interference. What's the rest of the story, you ask? Well, that's entropy. Entropy is the rest of the story for a chemical system, and is the whole story from the perspective of the universe. All thermodynamically favored processes increase the entropy of the universe. That's called the second law of thermodynamics. Before we get into all that, let's talk about entropy. Entropy can be thought of as a measure of the molecular randomness, or disorder, for a system. It is abbreviated with a capital S, probably because of its close relationship to the spontaneity of a process. We'll be focusing on a kind of entropy called positional entropy. Positional entropy tends to increase from a solid to a liquid to a gas. This is because solids are extremely ordered, low entropy, and gases are extremely disordered, high entropy. The more positions available to the particles, like when they're spread out as individual gas molecules, the more entropy the particles have. The tendency for soluble things to mix is due to the increased volume available to the particles. With greater volume comes a greater number of positions available for particles. If there are a greater number of available positions, entropy increases for the system. This increase in entropy is why solution formation is thermodynamically favored for soluble substances. Let's predict the sign of entropy change for each of the following processes. You can pause here and make your predictions. Did you pause? Anyway, when solid sugar is added to water to form a solution, the entropy increases, so delta S would be greater than 0. The final mixed state has more entropy than the initial unmixed state. This is because of the greater positional entropy available to the sugar molecules when they're separated from a crystal lattice into individual molecules. When iodine vapor changes from a gas to a solid, it becomes much less disordered, so delta S would be less than 0. The final crystal lattice arrangement has less entropy than the initial gaseous state of individual molecules all spread out from one another. The second law of thermodynamics states that in any thermodynamically favored process, there will always be an increase in the entropy of the universe. In other words, the universe favors an increase in entropy. Stuff happens because the stuff that happens increases entropy. This is definitely not a conservation law, like the first law of thermodynamics, the law of conservation of energy. It's important to keep in mind that the entropy of the system may not always increase, because the universe is more than just the chemical or physical change that we're considering. The change in entropy of the universe is the sum of the system's entropy change and the surroundings entropy change. Overall, though, if delta S of the universe is positive for a process, then it's thermodynamically favored in the forward direction. If negative, then it's thermodynamically favored in the reverse direction. And if delta S is equal to 0, then the process is at equilibrium, which thermodynamically means that neither direction is more favored than the other. So here's something for you to consider. In a living cell, large complex molecules are often assembled from smaller, simpler molecules. Is this biological process consistent with the second law of thermodynamics? Think about that one for a bit. We'll come back to it next time.